Awesome. So I'm going to be today's discussant. So I will share my screen, and then I'll also use this as an opportunity just to introduce Atticus. So Atticus Geiger was a PhD student at Stanford. Is that right, Atticus? You're done now?
Yep. Finished in the fall.
Awesome. Great. And Atticus, I'm very excited for this talk, and I'm really, really excited we got to have him here today. This is a topic that's near and dear to my heart. If you know me, you've heard me talk about causal abstraction, and Atticus has done amazing work in this space. So today he'll be talking about uncovering and inducing interpretable causal structure in deep learning models. So what is this, and how does this relate to the world we've been in so far? So except for the most recent line of talks that we had, we've pretty much been in this world where the statistical model is that there's some underlying SCM M over some latent variables or high-level abstract concepts. And there's some mixing function by which we end up getting our observations. And typically this mixing function is nonlinear, and it yields very complex observations like this excellent generated image of cows. And the target of inference is to learn the mapping, the inverse mapping from observations to these high-level causal variables. And this task, this is what is causal representation learning. And to summarize our goals here, we would like to identify, in a statistical sense, the SCMM as well as the causal variables, so the mapping function from X to Z. And we're okay with some benign indeterminacies here. So we know we won't be able to pin down the exact mapping function and the exact M, but we'd like to have our indeterminacies be up to things like permutation and things that essentially maintain the semantics of the variables. And what we've really seen so far is that to achieve this goal, especially for nonlinear mixing functions, we need some form of weak supervision from counterfactual samples or multiple heterogeneous data sets, so on and so forth. But the high-level thing I'd like to emphasize is that in our world so far, really the goal has been to learn some notion of meaningful features from unlabeled data. Okay? And I argue that where we're going, it's not so different. Okay? There's a different kind of model, but still we're trying to figure out whether low-level measurements capture some meaningful concepts. And the model here is going to be that there's some low-level measurements governed by some SCM M1. There's some high-level macro variables governed by a different SCM M2. And now our target of inference, or the question we're going to ask is, given some mapping function, given a candidate mapping, is there an equivalence between these two models, M1 and M2? And what we're going to do is assess whether every low-level intervention that we care about has some equivalent intervention at the high level so that they lead to the same counterfactual outcome when we apply the mapping function. Okay? So this is causal abstraction, but again, my hot take, or rather, not super hot take here, is that actually CRL and causal abstraction are not so different. They're in spirit trying to achieve the same goal of trying to find meaningful concepts from low-level data. And Atticus's work, and I think what he'll be covering quite a lot of in today's talk, is to learn flexible mapping functions to find alignments between neural networks and high-level programs of tasks. And so the cool trick here, the innovation, is to view neural networks now as abstractions of programs, computer programs, that solve different kinds of tasks. And so potentially this exact image will show up in today's talk, but here's just one example of a program that calculates Boolean equality on one side and a putative causal abstraction to some kind of neural network that computes the same exact task. And so with that, I will leave Atticus to dive into his work. Thank you, Atticus, for being with us today. We're really, really excited. Okay.
Sweet. Yeah, thanks so much for that introduction. I think, yeah, it's set the stage quite nicely for what we'll be talking about. And yeah, I really do agree with there being like very deep connections between causal representation learning and causal abstraction. And yeah, but yeah, and I guess I'll highlight that the setting of like network interpretability we'll have some like interesting, weird, like kind of differences or idiosyncrasies from maybe like the usual like analysis of like causal systems that you might be used to. So yeah, hopefully this will be fun. Yeah, and as I go through out these slides, I'd say feel free, especially during like the explanatory examples I have, throw out a question or if you'd like to. No, I'd encourage that. Cool. All right, so I'm going to be talking about uncovering and inducing interpretable causal structure in deep learning models. So this is what I've been focused on for my entire PhD, and it involves lots of other great collaborators at Stanford and other places. So yeah, check out the papers and, kudos to them for being such great collaborators. All right, so I'm going to start by just talking about how I view interpretability, sort of like through the lens of causal abstraction. So, zooming out a lot, there are certain kinds of dynamical systems in the world where the way we want to approach understanding those systems is by saying they implement some sort of algorithm. So, when a human does mental math, or really maybe anything, you might think that they're implementing some sort of algorithm in their brain. So in mental math, it's just some sort of like very simple, like arithmetical computation. So if you have a deep learning model that's doing some sort of logical reasoning, like you might similarly infer that there's some inference algorithm that's being run. And then I think the most sort of canonical example of this that no one can disagree with, you have a physical computer. It's a very complex low-level system with like very simple low-level operators, but clearly the like assembly code and then the Python programs we write are different levels of descriptions of that underlying causal system. And so the sort of philosophical issue that you initially kind of like confront here is that in cognitive science or AI or like the philosophy of computation, there was never really sort of like an agreement on how to mathematically ground out this notion of an algorithm being implemented in some dynamical system. And basically, I think causal abstraction is the sort of like answer for how you go about grounding that relationship precisely. And so the solution is you represent any of these dynamical systems with some sort of causal model that you can also that and you also represent the algorithm with the causal model, and then you cache out the relation of implementation in terms of causal abstraction. And then to sort of verify this experimentally, what you do is you perform interventions on the low-level system and interventions on the high-level system. And if your mapping is a good mapping, then the outcomes of those interventions will be aligned by your mapping. And we'll get into the details of that. So originally, causal abstraction has sort of origins in like weather data analysis. Frederick Eberhardt's doing like causal feature learning on all sorts of like brain data. And all my work is on artificial neural networks. And so what is causal abstraction in like a layman's sentence? It's sort of the process of aggregating or simplifying a system with a bunch of micro variables into a simpler system with a small number of macro variables. And so that's just essentially what we mean when we're talking about abstraction. And so why I think modern AI interpretability is kind of like the most exciting and cool place to be doing these sorts of experiments is, so when we talk about like the brains or weather, really you're in the sort of usual setting where you have observational, at most some weak interventional data about what's going on in these systems, and then you're trying to sort of reconstruct this multi-level picture of what is going on. But the really cool thing about modern artificial neural networks is that you have them in the ideal scientific setting. You can run them forward, backward, do whatever you want to them. You have perfect readouts of the states and the interventions. And so this is where I'll kind of highlight where this is really not the usual setting for people who are used to like, just causal representation learning or causality in general, where we have a deterministic system a lot of the time. And even if it is non-deterministic, like it has some sort of temperature or probability to it, we understand the probability perfectly where it's coming from, and we can control the exogenous variables as well. And so yeah, we're really in this sort of like perfect scientific setting, like a little little lab where we can do absolutely anything we want. And so it's really a matter of like, do we have the sort of like, do we have the methodology and the theory to support understanding the system when we have perfect access to it? And a connection I kind of like to make, there's this paper by Conrad Cording and Eric Jonas that was like, can a neuroscientist understand a microprocessor? And basically the whole contention of that paper was like, not really. Like, we don't have the setting of like looking at a microprocessor. Like, that's just so far away from the sort of data we get. We don't even have the tools to sort of go about analyzing it. And I really view this line of work that we're going to be talking about today as kind of like making progress on that like sort of pointed out question. So yeah. Yeah, and then here's a cute little figure, just like where does interpretability sort of fit into like a larger picture of explainable AI? So there's questions like, the real world, results in data being generated and people making these models, and then human decision makers need to like make decisions about these models and do things with them. And what interpretability is about is really narrowing in on the relationship between some sort of transparent algorithm where the variables have intuitive conceptual quantities and how does it relate to the underlying system that is a black box, highly connected system with lots of little microvariables. Cool. So yeah, first we're just gonna walk through a kind of like simple example of the kind of analysis that we've been doing, and this would be a place we can have some questions and just make sure we get a good grip on what's going on. All right, so interchange interventions. So a sort of like very natural question is, so if abstraction is a matter of verifying that interventions at a low level system are going to have the same effect as interventions at a high level system, what are the sorts of interventions that we want to consider? And what I'd say is if you're just trying to analyze an object, and this object is an input-output system, so you just have a space of possible inputs, it produces outputs, you should at least be considering interventions that will sort of stay on the data manifold induced by that input structure. Meaning, if you intervene on a representation, you should set it to be a value it actually takes for some other input. And that's the core idea of what an interchange intervention is. So the recipe, we state a hypothesis about an aspect of some neural network's causal structure. We choose an alignment, and we'll skip over how we go about choosing that alignment until later. But say we just know like this high-level variable is located in this neural representation, and then we do interchange interventions. So we do these types of interventions at the high level and the low level, and then we see whether the same thing happens at both levels. So here's the little example we'll be walking through. So on the left side, we have just a high-level hypothesis. All right, so the task is just adding together three numbers, x, y, z. The output is just the sum of those three numbers. On the right side, we have this black box neural network. It's been trained on the data set, and it solves it perfectly. On the left side, we have an intuitive hypothesis. There's probably only about three for this one, which is we think it adds together x plus y first. So it creates this variable s1. It's the sum of x plus y. And we think the network is doing this. And more specifically, we have these dotted lines saying there's an alignment between the high-level model and the network. So we think the network is doing this and storing it in this location. So S1 lives here. And then W, which is just a copy of Z, lives here. And that's the sort of like hypothesis we have about where information is being stored in the network. So if we wanted to test our hypothesis about S1, what we do is we would run an interchange intervention at the high level. So input 1, 2, 3, we get this intermediate state and the output of 6. The other input is 4, 5, 6. We get an intermediate state of 9 and 6, the output 15. And so interchange intervention would say, take this S1 and replace it with the value it takes on a different run. So then what does that do? It increases the output by 6. And so if we think that S1 lives here in the neural network, we should be able to take the two same inputs, run them through the network, replace the representation at this location, and then the output of the network should be 12, matching the counterfactual output of the high-level model. And so this is just an example with one pair of inputs, but really what the meaningful causal abstraction relationship is here is if for all pairs of inputs, we can do these manipulations on the low level model and the high level model, and they always agree on their outputs, then we say we have like a perfect abstraction relationship between these two systems. This is indeed exactly what the network is doing, and this is where S1 is being stored. So I can pause here for a moment in case any questions.
I can ask one. So this is really relying on what you said at the beginning, though, where you can rerun the network with, it's kind of counterfactual in the sense that you sort of can rerun the network with different inputs and swap things out. It's not sort of something that you could then. It's a neat idea. Like it's like it'd be tempting to sort of be able to apply these in the neurological systems and the various other places. But it feels like this is kind of specific to the ability to
100%.
rerun. Yeah.
Yeah, I think that's 100% the case. And like this is like, yeah, hyper idealized neuroscience, you might think of it. Like you'll never be able to do this with a brain. It's hard for me to even imagine what it would mean to sort of like, yeah, be able to neurochemically do this. But
Yeah. Okay.
Anyone else got a clarification or feeling good? Sweet. All
So
right.
maybe I have a question actually. So
Uh-huh. Yeah.
so I'm not trying to understand why you need to have like this, like why you need to have like two systems. Like why can't we just say like, you know, take like a given input and then just intervene on you know, the rightmost neuron. And yeah, so I'm not trying to understand like what do you gain by sort of introducing this other network and doing like this like this like taking the specific value from this other network.
Mhm.
Maybe I'm missing something, but
Yeah. So so that's sort of like why interchange interventions, why not just some other intervention that we could apply to the network? And so I think it's totally I would say the way I think about it is interchange interventions are if you're analyzing the system in itself, they're like the bare minimum of what you want to be able to analyze because these are the actual values taken. And for every value that's actually realized at this location, we need a function telling us what the value of S1 is given the value at this location. And so if this is the function and that function is going to be sort of in harmony with our intervention function that we're mapping from low level to high level, then this is just going to kind of like fall out that we need to support these kind of interventions. Like if this is indeed a robust mapping, like when we run 456, L1 is indeed a 9 representation here, then when we intervene and set then interventions that set other runs to have this 9 representation value need to treat it like a 9. Otherwise, the whole the system just kind of falls apart. As far as like, yeah, I'm not sure if that actually, yeah. But then the question of should we be able to support other interventions like and give them semantics at the low level? I definitely think we should. So like you might think I don't really care about analyzing the original system. I just want to do some sort of intervention that makes it as if I've changed this to be the value 9 and I don't care if it came from another actual run. And if that's the case, I think that's totally fine. You can just like sort of you could learn one like through gradient descent and figure out an intervention to perform, or just try one and see what its impact is in all these different situations to characterize what the sort of high level semantics of the value you chose is. So yeah.
okay, thanks.
Mm-hmm.
I guess that the premise here is also that the neural network is in fact implementing an algorithm rather than just doing some sort of function approximation, right?
Mm-hmm.
Like, and so that's the sort of starting point, right? So we have to accept that it's actually implementing an algorithm and storing variables in some place in some particular node. Is that right? Right?
Well, I wouldn't say we have to accept. I would say we're sort of investigating whether it is
We're
true.
testing
Like,
whether that, yeah, okay.
exactly. So that's definitely the original hypothesis, and there's definitely no guarantee that this is indeed the case. So like if this were like a program that is just like a dictionary structure where it's mapping directly from every possible input directly to the output that has no meaningful internal structure, then you would never be able to find a successful alignment that would actually get sort of high accuracy as far as like these interventions resulting in the same things.
Okay, so it's a way of falsifying this sort of claim that's the neural
Yes.
network's implementing an algorithm.
Yep.
Uh,
Yeah, this is how you
okay.
go about falsifying the
Good,
claim.
good.
Yeah.
Okay.
I can go next. So for formally testing whether or not such an algorithm exists, the number of hypotheses could be prohibitively large, right? Because you can consider individual neurons or like different combinations of neurons. So
Mm-hmm.
it's very hard to figure out what's good hypothesis to test because you can't possibly test all of them. Is that true?
Yeah, I would say it's true in two different ways. So one, the high level model is like, so the space of possible high level models is really the space of possible algorithms that have an input output behavior, which is in principle like infinite. In this case, there's not that many interesting ones, but even if you get to something like sorting a list of like 5 elements, you have a lot of really interesting, complicated, different ways of doing that. The second way in which it's very hard to come up with a hypothesis is even if you fix your high-level model, then you have to go about choosing where each variable is localized inside the network. And then that is also a huge combinatoric space. But we do have some good news later on for that one, and like some ways of automatically learning this using gradient descent, which will be very cool.
Awesome, thanks.
Sweet. Yeah, thanks for the questions here. All right, I'm gonna move on to, yeah, whatever happens next. Yeah, okay. So I'll just briefly go through, like, just kind of like highlight a couple of things we applied this on, but not going to go into the details of the experiments. So the first sort of like experiments I was doing was on natural language inference. So the sort of quantities that we were looking for, the variables, were entailment relationships between words. So like flowers are plants, but plants aren't flowers. So plants are like a more generic term than flowers. So that was the sort of variable we were looking for. Like, can we localize this information about lexical entailment to some representation in the network? Yeah, and this is like the sort of little very simple program you could think was solving this because negation flips lexical entailment. I won't explain that. Yeah, this is kind of what the interchange intervention looks like in this natural language setting where elm entails tree, pug entails dog. So the relationships are flipped, and then you do an intervention that will replace this reverse entailment relation with a forward entailment relation, and this should flip the label. Again, I won't go into the details on this. You can read the paper if you're interested. We did this in a way more complicated setting on this like very complex logical inference data set that I made. It's like automatically generated with lots of quantifiers and negation and stuff. And it has this like very complicated high-level tree structure that to date we still haven't actually gone back with the new pool tools we have and do a really the robust analysis of what was going on in this network. So yeah. Yeah, I guess something I'll just highlight here. So something people do in like AI interpretability stuff is they train probes. So just doing basic correlational analysis of things where they train some tiny model to predict out the value of a concept from a neural representation. And in general, I think that method is like pretty uninteresting when it comes to actually trying to understand what's going on in the network. And across the time, we've accumulated plenty of heat maps that are things like if you probe, everything lights up like crazy when you probe. It's like you can kind of get information out from anywhere. And then if you're doing interventions, it just looks a lot more discriminative and sparse, which is just like broad visual evidence that we'll leave at that. That correlational analysis is bad, but I don't probably need to convince anyone of that. Yeah, so then inducing causal structure. So something that's pretty cool about this whole setup is that before we're in this sort of like falsifying high level hypothesis mode, but something else you can do is actually, is use the high level hypothesis as a source of supervision during training of the network. And so you can use interchange interventions during the gradient descent process and update the neural network to have a particular modular high level structure. And so this is sort of like if you had like the interchange intervention operation is from like the previous slide, but these red lines are the gradient descent updates going. So if we're receiving supervision at this sort of counterfactual output of the network, the red lines are saying, okay, we're going to send this signal down the network like usual, but when you reach the intervention site, it's going to jump to this other run of the network and continue down this second run. So it's actually pretty distinctive, like unique update where you have these sort of like parallel systems going on, and a lot of the weights are getting double updated based on what occurred. And so, yeah, it's a cute use of this sort of like framework, and nothing really has to change to support this kind of thing. Yeah.
I think Danya had a question.
Yeah, that'd be great. That'd be great. I just quick question about ITT.
Uh-huh.
Here, can you posit any alignment between the variables that you wish, since you're going to be training the neural network anyways to have this kind of consistency?
Yeah, yes, that's totally correct. And then there's usually a lot of different alignments that are going to be successful, and some which are going to not be successful due to things like you don't give it enough room to compute the variable you're asking it to, or something like that. Or there's something about the architecture that inherently localizes pieces of information, and you can't force it to move them around in the way you're asking.
Perfect. Great. Thank you so much.
Mm-hmm.
Yeah, I think I was going to ask a related question, which is like, you're surely bounded by, the computational ability of the neural network. You can't sort of do an exponential time algorithm in a linear time,
Yeah, no,
forecast
definitely
neural
not.
network. But like if you're sort of within the constraints of the neural network, this is then saying I can force the neural network to implement the particular algorithm I want.
Mm-hmm.
Can you then do the same falsification step? Like, could you then ask kind of, is it possible to implement a particular algorithm in the neural network, or is that something that should just be done analytically rather than?
Oh yeah, you can definitely do that step, and I think that's sort of like a in the analysis mode, you could think that's like a sanity check that your analysis is worth doing at all. Like if you can't force the network to do what you're curious if it does, then it probably can't do it.
I see. Yep.
Yeah, and okay, yeah, we're still super good on time. Yeah, any other questions? Cool. I'll just walk through a couple of like random highlights. Again, not explaining that much about what it's actually doing. So here is the sort of like there's this sort of task that someone created that is just using 4 MNIST images, so just handwriting samples, and then the task is the top left image, whatever value it is going to tell you which of the other 3 images is the correct label. So it's just very simple, sort of like symbolic structure to how to solve this task. And we do sort of interchange intervention training updates to solve this task under like a very difficult generalization split. So the point of like the thing highlighted in the original paper is that you can use sort of like these internal interventions during training to simulate being, so just sort of get more signal out of your training data, sort of like put you in more situations than your training data actually supports, because you're computing these sort of like intervention counterfactual situations that don't actually occur in any of your training data examples. And we also do this for this sort of like, it looks like a little reinforcement learning setting, but people just train like transformer models on it. And it's yeah, we do sort of like a similar thing where they have this systematic generalization task where they're like holding out particular scenarios, but by doing internal interventions to sort of simulate things that don't actually occur in the training data, just using the training data, yeah, you can sort of like get good generalization on these tasks. Yeah. Another thing we use this for is for model distillation. So this is like a very straightforward application. It's kind of a weird application of this, and where it's actually no longer like the small model is guiding the big model. In this case, it was the big model is guiding the small model, and we basically just added sort of like an interchange intervention training term to the loss of distillation objectives, and that seemed to be helpful broadly. And then a last thing we did was, all right, this one's pretty cute as well. So we created this data set called Kebab, which is all about like causal estimation, but in the setting of like neural networks. So how does a particular change to the input data generating process affect the output of the network? So in this case, we had these like restaurant reviews. These aren't the actual reviews. It's like a simplified figure, and they had different aspects to them. So was the food good? Was the service good? Was the ambiance good? Was the noise level good? And then those are binary sentiment variables. And then the final outcome of the network is just a 5-star rating of the restaurant. And so the question is, what will the impact of changing food from positive to negative be on the 5-star rating of the model? And the best method we have for this benchmark was using interchange intervention training to take the original model and then create a model that's as close to the original, but supports internal counterfactuals. So it localizes these concepts of food sentiment, service sentiment, to particular locations in the network, and then we do interventions on those to simulate the input counterfactuals that we're curious about. And that's sort of the state of the art as far as like solving this benchmark on causal effect estimation. And so, yeah, the interchange intervention training, I think it has, it's very interesting and has like a weird smattering of use cases so far. Yeah, and then I think a really nice little fact about this network is that it is induced to have these localized concepts is you can do integrated gradients, but do them mediated through where we localize the concepts. And so you can take like the review and say like if you do integrated gradients, saying like what was the most important thing for getting the star rating, but only relative to food, so mediating through where we localize the food concept, you can see like say this row highlights delicious pasta, but it doesn't highlight friendly waiter or the other aspects as much. And that's just a sort of like cute application of what happens there. But yeah, but really I'll move on because I think the most exciting part is next. So distributed alignment search is where really the question that I was asked earlier about like how sort of like expensive and intractable the problem is of searching through the hypothesis space. So this is the method that we have for actually learning. If you have a high level model you're interested in and you want to learn where the concepts are located in the neural network, then this is going to be the method that is sort of like very exciting and cool. So the basic starting point is the figure that Danya showed at the beginning, which is this very simple network. So the task is just Boolean conjunction on the left side. And so this is a very simple program. All it's doing is taking P, taking Q, and then storing them. There's nothing happening at all at this middle layer. And then it just computes the conjunction of the two. And so a network that does this, if you represent true as 1 and false as -1 or 0, I forget actually which, but then the weight network is just an identity matrix, so it's just moving x1 to h1, x2 to h2, and then the output has a negative bias term, so basically like if they're both true, it'll push it above this bias threshold and it will output true, otherwise it will output false. So if you didn't understand that, that's fine. You can just believe me that this is a very simple, like canonical example of like these two objects doing like the exact same thing under this alignment. So H1 and V1 are the same thing, they just copy. H2 and V2 are the same thing, they just copy. And that's what the identity matrix is doing here. So something you can do though is what if you, instead of having it be the identity matrix, you just slightly rotate this information. So instead of identity matrix, it's a rotation matrix of 20 degrees. So just a fact is the input-output behavior is still completely preserved in this model. It still computes the conjunction program for all 4 inputs. But something that is interesting is it no longer has this abstraction relationship where H1 perfectly represents V1 and H2 perfectly represents V2, because this information has sort of been tilted, we're off axis, and they just don't align, these two quantities. And so there's a failure case in interchange interventions. So at the high level, if you do true, true, and false, true, and you replace V1 to be what it is on this run, then you get the output true. But if you do the same thing with H1 on the network, you get the output false. And the values here aren't important, but this is just an example of why this hypothesis is falsified under this current alignment. And so what we then want to do instead is say, well, clearly X1 and X2 are being stored in H1 and H2 in a way that's perfectly recoverable. It's just on a different coordinate system, namely one that is just rotated by 20 degrees. So if we can look at these hidden representations, this vector of two values, under a non-standard basis that just rotates by minus 20 degrees, this will be, viewing the information here, it'll be exactly what it was in the original case with the identity matrix. And so this is a very tiny motivating example for why you might want to think about neural representations in a non-standard basis. And another way of saying things is instead of looking for a concept being stored in a neuron or a group of neurons, we're instead looking for it being stored in a linear subspace of a vector representation. So if you do some rotation of your coordinate system and you choose a set of dimensions in that new coordinate system, that is just a linear subspace of your original vector space. Yeah, and so interchange interventions don't target these things, and more broadly, if you just have a causal model, normal interventions won't be able to target these sort of variables that are distributed across several variables at once. And so our solution is to move to this new operation called distributed interchange interventions. And yeah, I'll explain what this figure is sort of supposed to be looking like. So the idea is these are 3 runs of the neural network, each with a different input. Green input, red input, blue input. At these 3 neurons, we get a vector representation that is here. So that is represented visually in each of these locations. So what we can do is we first apply a rotation matrix. So we get to some non-standard coordinate system. And the vectors stay the same vectors, but now the coordinate axes have been rotated. And we're in this new representation space. It's still 3-dimensional. Then we do our interchange intervention. So on the run with the red inputs, we replace the first dimension of this new rotated coordinate system to be the value it is for the green run. And then we replace the second variable, or the second dimension in this new rotated coordinate system with the value for the blue run. And then we get this new brown vector, which consists of the green y1 dimension, the blue y2 dimension, and the red y3 dimension. Then what we do is we apply the inverse rotation to get back to the original coordinate system. And we plug this round vector into the network and run it the rest of the way. And so this is a multi-source interchange intervention where we are taking green and blue are our runs to generate the intervention values. And then we're targeting these variables that aren't in our original coordinate system, but instead in some rotated coordinate system. And then we're running the network the rest of the way forward. So broadly, the operation is, and really this notion of a distributed intervention doesn't have to just be for rotations. If you have any invertible function that brings you into some new variable space, you can say, apply the invertible function, do your intervention, then apply the inverse of that invertible function to get back to your original variable space. And that's just like a coherent intervention operator you can define on causal models. And so that's the sort of key innovation that allows us to start talking about, in like theoretical way, targeting these quantities that are not in the original variable, however the original causal model carved up its variable space. It's like, suppose we had an alternative variable space and we did interventions there, but then we came back to our original variable space. And that's like a way of talking about or thinking about what's going on.
Do you have a intuition for, like, because you were able to successfully do this a little bit, do interchange interventions before you had this, but it's sort of surprising to me, like that worked at all in some sense, you know, like because distributed representations are sort of such a default mode of operation for neural networks.
Yeah.
Do you have some sense of like sort of why you were able to successfully do it without this?
So that's a really good question, actually. And so a lot of the original success cases are, it's not even like, I'd say it's less like thinking about them as like we found individual neurons, and that's not even like what we ended up doing in a lot of cases. A lot of times, if you're familiar with transformer architectures, it's like we target, so like if you can visualize, it's just a grid, like each token is a column of this grid, and each row is a layer of the transformer architecture, and we would just target some row column location, so the entire vector for a particular token, and swap it out. And there absolutely are reasons that this architecture targets at this level of modularity, sort of like chunks of neurons. But when it comes to individual dimensions within those vectors, yeah, I don't think there is any real reason they should. And like to the degree that they are, my guess is they're kind of like, I don't know, happenstance, like only exist insofar as they like happen to hit be an essential dimension like inside some like linear subspace would be my guess.
Yeah. I mean, they're sort of one or two. It's almost like the exception rather than the rule. Like the exceptions are
Exactly.
interesting. There was that like sentiment neuron that.
Exactly. Yeah.
Yeah. But yeah. Okay, good. But the transformer makes sense. That's more, makes because
Yeah, no, definitely. It's a very good question because it's there are particular sort of like chunks of the architectures that are very intuitive for information to be stored in. But once you get to the individual vectors, the way transformers work, when the attention or the MLP layers are writing to or reading out from this sort of like residual stream that exists in a transformer that's flowing throughout, they're always doing this using linear transformations. So they read out information with linear transformation and they write in information with linear transformation. So really, like lots of people think that linear representations are going to be the right way to think about information in a network. And so these are the sorts of interventions you want to be doing if that's what you think information is going to be stored like.
Gotcha.
Yeah, and so just quickly finishing the example we had. So instead of, this is what our alignment now looks like, where we're not aligning with the variables in the original network, but instead we have this function bringing us into this new system, new coordinate system, and then we're aligning with the variables in this transformed space. And if you do that, then we've recovered the perfect relationship again. And the original failure case that we had is going to be successful because once we've applied these inverse rotations, then we just get 1, 0, 1, 1. They look super pretty and nice again. So in the original system, they now are like negative 3.4 and 0.94 because we've applied this messy rotation to a very simple network. But if we apply the inverse rotation, we get into the pretty variable space, we do the interventions, we go back to the ugly variable space, and then we run it forward. And the counterfactual prediction is true, and this works for all 16 interchange interventions on this toy example. And so then the sort of like, so this is like a cool, just like generalization of like the tools, but then the really exciting sort of thing that makes the hypothesis search now way more tractable is that you can just learn this rotation matrix using gradient descent. So if you just treat the rotation matrix as the parameters that you want to learn, you freeze the underlying network and you use your high-level hypothesis as a source of supervision. So what you can do is say, I don't know where H1 is, but let's just say it lives in Y1. When you initialize the rotation matrix randomly, this will be wrong. So treating Y1 like it is H1, or sorry, like it is V1. Sorry, I don't know where V1 lives, but I'm just going to say it lives in Y1. Treating it like that originally with a randomly initialized rotation matrix will be wrong. You will get incorrect sort of like counterfactuals from the high and low level. But when you run the counterfactuals at the high and low level, you can use the high level output as a source of supervision saying, update the rotation matrix so that the intervention I did is closer to having the outcome that I wanted it to, according to my hypothesis. And so if you do this for a whole training data set and continually update this rotation matrix, it will, if it's possible, move information from H1 and H2 to Y1 in a way that will succeed and sort of reveal the abstraction relationship between the models. Of course, this isn't guaranteed to happen in general, but yeah, that's the sort of idea. Yeah. Oh, question. Yeah.
Thanks. Is it very likely that in the adversarial case, there might be different rotations that could make it look like you're matching multiple hypotheses, like multiple algorithms?
There are two, yeah, I guess there are two parts to the answer to that question. One is that it'll depend on whether these different algorithms, I think, are logically sort of mutually exclusive from each other. Like some high-level hypotheses will be compatible with one another. Like if you have like you're adding together X, Y, Z, and W, and you say like X and Y sum exists. That's one hypothesis. Your other hypothesis is the Y and W sum exists. Those are totally compatible with each other, and one rotation matrix might solve both. But if you have the hypothesis X and Y exists, and then Y and Z exists in the same representation, I think that's logically impossible, but I'm not sure. I mean, that's like that is a good question, whether or not you can get two sort of different algorithms to look like that at the high level. My intuition says like if there's going to be some like contradiction that occurs if you're saying like the same chunk of information contains both of these like different quantities, that like some interventions will have to fail for one or the other, so you're not going to have a perfect relationship between the two. But I actually think this gets incredibly dicey once you give up perfect relationships and instead start talking about approximate relationships where say like 70% of the interventions are correct. You could totally have two competing hypotheses that are contradictory with each other have both like 70% of them work, because maybe the 30% that they don't work on are the crucial sort of like interventions that are actually distinguishing between the two hypotheses.
Thanks.
Yeah, other questions?
I think Chandler.
Yeah. First, I'll send something to the chat that might be related to that question of whether there would be any contradictions in like the kind of information that can get stored. I kind of see that as like that should be approachable as like an identifiability question. But then the question was on this slide, when you have to do learning the rotation matrix, are there any tricks to the parameterization of that or any kind of implementation details that are worth mentioning?
Yeah, that's a good question. So the first I'll use an opportunity to highlight to advertise PyVean, which is this PyTorch library, like PyTorch based library that my collaborator Zen Wu has led the implementation on, and I've been working on as well. And this sort of like has a bunch of these tools and type of analysis things set up for us. But yeah, I mean, originally all we did was sort of like go into PyTorch and just do like dot orthogonal, and then that works as far as like the thing, yeah, getting off
So
the
nothing
ground.
too subtle.
Yeah, nothing too subtle. I think this is definitely a place where there is like loads of room for thought. Like I don't know, doesn't seem like a hugely hot topic like orthogonal sort of optimization as a thing. So I would absolutely guess there are going to be major speed ups if people who know more than me about the linear algebra and the like actual low level optimization process were to look into this. I think we had another question. Yeah, David.
I think I'm more looking for a clarification. So the learnability of this alignment, does it depend on some sort of approximate equivariance from the input and output? And particularly, does it require the known equivariant, the sense of equivariant of the specific algorithm that you try to align?
So the high-level algorithm, low-level algorithm, the high-level algorithm and the low-level network are going to have the same input-output behavior for the abstraction relationship to hold. But as far as like whether we need to know that there's like this interventional equivariance across the two systems, that is a hypothesis that we are going about trying to falsify. In this case, actually, yeah. So in this case, like actually maybe falsification is the wrong language for this. So in the original setting we were talking about, falsification was right because if we got a wrong intervention, then our alignment is incorrect. But in this case, really, it's like we're searching for an alignment that is good. And if we don't find one, we have no guarantee that like that was theoretically impossible to do. It's sort of like inductive negative evidence that there probably isn't an alignment if the optimization process fails, but we aren't sort of logically guaranteed to find the optimal rotation if it exists.
I see. Thank you.
Yeah. Yeah. And in the most sort of like aggressive settings where you have tiny networks, you can apply a rotation matrix, say to like the entire layer of a transformer and look for any like pick up information from anywhere across the whole residual stream. But once you get to like remotely large cases, the rotation matrix will end up like getting way too large. And so what we end up doing is usually targeting specific vector representations, applying a rotation matrix to them to sort of look for a linear subspace inside that vector representation. Yeah. Yeah, so, and the TLDR on this method is it works pretty well and has some very exciting sort of like applications already. Like we've had like lots of follow-up projects, like, and people starting to use the distributed alignment search to sort of do interpretability analysis of networks. In the original paper, one of the cleanest examples we have is this like very simple hierarchical equality task where it's just 4 inputs and the task is just, are these first 2 inputs equal? True or false? Are the second 2 inputs equal? True or false? Are these 2 true or false values equal? True or false? So it's just a very simple little algorithm, and there's an obvious symbolic solution to it, like at the high level. It's compute these 2 variables. And we are able to apply distributed alignment search and find in the first layer that you can just find a rotation matrix. And this is like an MLP we train on this, so it just feed forward with nonlinearities. But we're able to rotate the first layer and just have 2 perfect halves. Like one represents one variable, one represents the other variable. Depending on who you are, like if you're Gary Marcus, this might really anger you and go against everything you believe. But if you're like a lot of machine learning people today, this wouldn't be that surprising to you. People think that like, yeah, sort of symbolic like thing can totally occur in neural networks. So yeah, but I think this is a nice sort of like clean example where the answer as far as like to what degree do neural networks implement symbol looking things, the answer is definitely not absolutely 0. The answer at least has to include this small example. There's like a little tree structured thing going on here. And when I think about that sort of broad question, like to what degree do neural networks implement symbolic, compositional, systematic type processes, I think it's going to be like a spectrum that we have to characterize from like being a lookup table, like a Python dictionary, all the way to being like, you know, the human brain or whatever we think is the canonical example of the most systematic, compositional, symbolic type thing. And yeah, I think these are the sorts of tools we'll want to use to investigate that question and sort of characterize where we are on that spectrum for any given model.
Do you have any thoughts on how scale impacts where you fall on that spectrum? Right. So yeah.
Oh,
yeah.
I mean, like, I feel like my answer won't be that exciting, but it's probably just like clearly scale behaviorally moves you up that spectrum as far as behavioral analysis goes. And my strong hot take is that I think like incredibly complex, interesting behaviors, being able to learn those is almost certainly going to like have some underlying like interesting systematic process to how you're solving those tasks. And so my answer would be, my gut take is, yeah, like as you go up in scale, because you see these qualitative shifts in intelligent behavior, you will see qualitative shifts in the amount of interesting compositional symbolic structure that underlies the behaviors.
Yeah, I guess the sort of sense in which I asked the question is like, as we scale up, you're forced, the sort of capacity to like do the lookup table thing becomes harder and harder, right? You sort of have to, it becomes easier to solve the process by actually just implementing the algorithm than by trying to memorize all the input output relationships. Especially sort of as you scale across more heterogeneous data and more sort of scaling across multiple different kinds of distributions.
Yeah,
permanent
so as you scale
environments.
up in data, that's true, but there's also a competition on the other end, where as you scale up in parameter size and model size, your lookup tables can get bigger and bigger.
Can be bigger. Yeah.
Yeah.
Okay. Yeah.
Is there anything else interesting in this? Boundless DAS. So there's a parameterization of DAS. So one hyperparameter we had was like the size of the linear subspace. We have some relaxation of that hyperparameter where we can learn this sort of sliding scale for how big the linear subspace is in dimensions that we want to be targeting. You can also do interchange intervention training with DAS. So just targeting linear subspaces instead. Yeah, I'll just sneak in one last comment, which is we have this cool benchmark Ravel where we're actually starting to systematically compare different methods for localizing concepts, which is something I think interpretability that kind of sorely needs. Like there's a lot of very idiosyncratic work focused on like tiny toy behaviors, and we're starting to try to get systematic evaluations of like what does it mean to have a good tool, what sort of problems should it solve, and how do we compare things like DAS with autoencoders or like differentiable binary masking, which kind of learns individual neurons that try to represent information.